When different cores in a computer have access to different caches, but are accessing the same memory locations, there is a risk of cache incoherence. Whenever a core accesses a memory location, that location's data is copied into its cache. Multi-threaded programs make frequent use of shared data to work on tasks. But for this to work, the modifications made by one core to a memory address must be visible to others. However, this is not how it really happens. When a line of code modifies the contents of memory, it does not necessarily mean that the memory is modified right away. Modern machines typically only modify the copy of memory that is in their cache. Then they wait until later to write those changes back to memory. Fewer writebacks generally means faster performance since cache is so much faster than RAM. But what if two cores are modifying the same data in their own caches? Clearly, this can cause problems, because these values are inconsistent. They don't match. This video deals with an approach to cache coherence that is a form of snoopy protocol. The protocol is snoopy because each cache snoops on or listens to signals that get sent back and forth to each other so that they can determine what to do. Such protocols can be either write invalidate or write update. A protocol is write invalidate if the cache will mark its own copies of data as invalid if they snoop a write being performed on that same data in another cache. So in this example, this cache modified what was originally 7 to a 4, and this cache would snoop that change and invalidate its copy of that data. However, in a write update approach, each cache gets updated whenever any one cache writes new data. So if this cache were to change its value to a 4, then this cache would snoop that change and immediately update its value to also be 4, even though the value in memory might not yet have been updated. So this second approach can lead to many updates that will ultimately end up being unnecessary. So we're going to focus on a write invalidate protocol. The specific focus of this video is the MESI protocol, which stands for Modified, Exclusive, Shared, and Invalid. These are the 4 states that any given line in a cache can be in. Different caches can contain data from the same memory address, but the state of that data may differ from cache to cache. Here is what each state means. So if a line in the cache is in a modified state, then within that particular cache, that line is valid. Yes. If a particular cache has exclusive access to some data, then within that cache, that data is valid. If that line is shared by one or more caches, then within each cache that has it in the shared state, the data is valid. It is only if it is in the invalid state that it is not valid, meaning that it can't be trusted and that if the CPU wants to read it or use it, it can't. Now, each line in the cache refers to a particular memory address. So if one cache has a cache line in a modified state, then the corresponding memory is going to be out of date. However, if a cache has exclusive access to memory but has not modified it yet, then that means that the cache matches memory, and so they're the same. The same is true if the data is shared among several caches. That means the exact same data is in each of the shared caches and also in memory. Now, in the case that the data in some cache is invalid, we kind of don't really know what the correspondence to memory is, but it doesn't matter because we wouldn't use the cache data for anything anyway. If one cache has data in a modified state, that means it cannot be in any other caches, so that's a no. Same thing with being exclusive. If one cache has the data in an exclusive state, then it is the only cache that has that data. No other cache does. Now, if a cache line is in a shared state, it is merely possible that the data exists in another cache. This is because you may have one point where multiple caches are sharing a line, and then one stops using it, but the other caches don't update from shared to exclusive, they just remain in shared. And then when the data is invalid, it might be shared, but it's not really relevant in that case. Finally, there's the question of what happens when that particular cache line is written to by one core. So if a core writes to a certain cache line that has a modified state, nothing happens because the data gets modified, but this is already known to be a modified cache line, so no updates have to occur anywhere else. Now, if the cache is in an exclusive state, that will cause it to change to a modified state, but because the cache line was exclusive to this one cache, we don't have to share that information. We can just update it from exclusive to modified without sending any information to the bus. Now, in the case that the data is shared, so this particular cache line is shared, possibly among several other caches, this requires us to go to the bus and update caches. So this is a signal that other caches can snoop on, and they need to know that the data that is shared is now going to be modified, and therefore their own copies will be invalidated. Now, if some data that's invalid is written to, then that'll just go straight to the bus. We can formalize the rules regarding when a cache line changes from one state to another with the use of a state transition diagram. We actually need two diagrams because a cache line can change states either based on an action that its own CPU performs or based on an action detected by snooping on other CPUs in the system. For starters, if a cache line is in an exclusive state and a read occurs, what we call a read hit, then that'll cause it to simply stay in this same state. RH is for read hit. Snooping caches won't respond to this because they can't contain a cache line that is exclusive to some other cache. Similarly, a modified cache line that experiences a read hit will also stay in that state. In fact, a modified cache line can even write to itself. That is a write hit. None of these changes matter to any of the other caches. Now, an exclusive cache line that experiences a write hit will transfer to the modified state. But because that cache line was only in this one cache, it won't affect any of the snooping caches. For a cache line in a shared state, a read hit will not change the state. So reading a shared line does not affect other caches at all. However, writing to that cache line will create issues for other caches. That line will go from shared to modified in that one particular cache as a result of the write hit. And we will send a signal to other caches that they can snoop on. So if the cache line was shared in this one cache, then there's probably some other cache where it is also in a shared state. But here, the transition will be to the invalid state as a result of a snoop hit on write. So a write was detected elsewhere, causing the shared line to go to an invalid state. Now, let's say that some cache has a given cache line in an exclusive state, but then some other cache reads that same memory address into its own cache. So the one cache that had it in an exclusive state would snoop that change. That would be a snoop hit on read. That causes a transition from exclusive in the one cache to shared, caused by a snoop hit on read. Now, previously, one cache had it in an exclusive state and no other cache had it. The cache that had it in the exclusive state was snooping and went into a shared state. The cache that went from not having it at all to also now having a copy of it will also be in the shared state. Now you can also have a situation where the only reason that a given cache reads in data is that it intends to modify it immediately. So it's going to read it in and then write to it to change it. This is known as a read with intent to modify, but in terms of the signals that get snooped around in the cache, it's the same as a snoop hit on write. So if one cache has a cache line in an exclusive state, and then some other cache does a read with intent to modify or read with intent to write, then the exclusive version will transition to an invalid state. And this will be a snoop hit on write, which is the same as a read with an intent to modify or an intent to write. For a snooping cache, the transitions out of the modified state are quite similar. If one cache has a cache line in a modified state and it detects some other cache trying to read it, that will be a snoop hit read and will go to the shared state. The only difference here is that that modified data will be copied back so that the new cache, which is sharing the data, can have an updated version of it. Similarly, if one cache has a modified cache line and then snoops another cache reading with an intent to modify or writing to it, that'll be a snoop hit write, and it'll go to the invalid state. All that's left are the transitions out of the invalid state for a CPU that's performing some sort of action, so a read or a write. Now, the only reason that an invalid cache line would remain in a cache is if it hadn't had a chance to be cleaned up yet. Because once data is invalid, there's no point in ever reading it or using it for anything. And in general, it can be safely replaced with other data that the program might need. So if a cache line is in an invalid state, it's sort of as if the cache data isn't really present in the cache at all. And so to some extent, you can think of transitions out of the invalid state as being similar to the transitions you get when you go from not having the data at all to having the data in a given cache. They're technically different, but ultimately the state you end up in is the same. So there's only two actions that you can perform, a write or a read, but the read can be a read of data that only one other cache has or that multiple other caches have. And so let's look at the write first. So if we try to write to a cache line that is either invalid or that we don't have, that's known as a write miss. And we will have to read the data in to then immediately modify it. But once we modify it, our cache will have a modified version of that data. So we'll go from invalid to modified as a result of a write miss. Now, if we try to read the data and we're going from no other cache having it to this cache being the only cache that has it, then we will end up in the exclusive state. And so that is a read miss, but in the exclusive case. However, if we read some data that is in other caches, then we will go from invalid to shared, and that is a read miss shared. Now that doesn't mean that the data was in a shared state in other caches. The data could have been in an exclusive state or a modified state in other caches. But at the point where this initiating cache does a read, it will cause that data to be shared both within this cache initiating the action and within a snooping cache that had access to it. And I almost forgot one more transition that happens when a snooping cache senses one of its shared lines being read. That is a snoop hit on read. But of course, if that line is shared, it's shared in other caches, some other cache reads to it, then in this snooping cache, it'll simply stay in the shared state, much the same way that in the initiating cache, it'll stay in the shared state whenever it does the read, because a read doesn't modify the contents, and so that doesn't require any state change. Let's finish this video up with a quick exercise. Let's say that a particular area of memory that would correspond to a cache line is absent in the caches for two CPUs. These CPUs will be issuing some actions. So CPU 2 will read the data from memory, and we can look at our diagram back here to see what happens. So I said that going from being totally absent was sort of like being in an invalid state. So if CPU 2 reads the data, and currently no other caches have that data, that will be a read miss exclusive. So that means CPU 2 will end up with that data in an exclusive state. Now CPU 1 still doesn't have the data, and so it's still absent there. At this point, CPU 2 can do more actions. It could write to the data, which is a write hit. That causes us to go from exclusive to modified. The data is still absent in CPU 1, so nothing matters to CPU 1 yet. But let's say that at this point, CPU 1 issues a read for that same data. So in this case, CPU 1 is the initiator, and it's going from absent, which is like being invalid, and it's doing a read. But when it does that read, the data exists elsewhere. So it is a read miss shared. So CPU 1 will have that data in a shared state. And CPU 2 isn't doing anything, but it does snoop that change. So a read occurred on CPU 1. CPU 2 is in the modified state, so it's over here. And we have a snoop hit read, which goes to the shared state. So the data will be in the shared state in both CPUs. Notice that the state in CPU 2 changed as a result of an action performed on CPU 1. Now, if CPU 1 does a write at this point, then it is the initiator. So we'll go from shared, we have a write hit, and we go to modified in CPU 1. Now for CPU 2, CPU 2 is snooping, and we have a snoop hit write. So in CPU 2, we'll go from shared to invalid. Now, even though this data is now invalid in CPU 2's cache, CPU2 could still issue a command that says set the data in that cache line equal to a brand new value. And so that would result in a read with intent to modify, which registers as a write. So that is a write miss. So CPU2 goes from invalid to modified, because it's going to issue a write command here. And CPU1 is currently in the modified state. It detects a snoop hit write, and it goes to an invalid state. And so this demonstrates the kind of transitions you can have. And importantly, you can have more than just these two CPUs and their caches interacting with each other. But you'll always have one CPU or cache that is initiating an action, and then the others snooping on that and responding accordingly. Now, one more nuance that's not really captured in this diagram is that at any given point, the CPU can choose to release a cache line back to memory, typically to allow data from some other area of memory to be read in, so to make room for that new data. And it can be from any state. So if data is in a modified state and the cache releases it, it'll be written back to memory to make sure memory is up to date. If data is invalid, shared, or exclusive, then when the cache releases it, nothing needs to happen. Memory is not modified. And because that cache line will no longer be in the cache at all, it doesn't have a state. It's simply absent. And so that's why there's no actual transition here, even though the contents of the cache would be changing under these circumstances.